With this video, we begin our unit on gases and properties of gases as described in Chapter 11 in your textbook. Let's begin with an outline. We will actually start by considering the first section of Chapter 10, which talks about gases and the kinetic molecular theory of matter. As you will see, this is crucial for understanding the remaining material in Chapter 11. We may come back to Chapter 10 later in the semester. We'll see how things go. In Chapter 11.1, we will talk about gases and pressure. What is pressure and why do gases exert pressure? In Chapter 11.2, we'll talk about the gas laws, separate mathematical relationships that tell how properties of gases are related to each other. In Chapter 11.3, we will combine those when we talk about gas volumes and the ideal gas law. We will see a single mathematical relationship that tells how all properties of gases are related to each other. And then finally, I will introduce some special topics on densities of gases and stoichiometry problems involving gases, because as you know, stoichiometry is my favorite part of all of chemistry. So let's begin by reviewing. What are the three major states of matter? You probably learned this early in elementary school. They are, of course, solid, liquid, and gas. Plasma is another state of matter, but because plasma involves atoms that have lost most of their electrons and no chemical bonds at all, it's not really part of chemistry, it's more part of physics. We're not really going to talk about plasma this year. So, how do solids, liquids, and gases differ? Well, if you think about this in terms of the submicroscopic scale, you will realize that what makes a solid, a liquid, and a gas different is essentially how far apart the particles are. And I'll show a diagram of that in this next page. Well, what influences whether particles stick together really tightly, as in a solid, or whether they're very far apart from each other, as in a gas? Well, clearly, that's going to depend upon the strength of the interparticle attractive forces, which we talked about a couple of units ago, and we'll come back to that later. So, here's a nice diagram I found online. Let's imagine a sample of some form of matter. Could be a metal, could be a non-metal, we don't know, but we're going to look at the physical state it occupies as a function of increasing energy. So at very low energy content, it will exist as a solid. The molecules that make it up are arranged in regular repeating patterns. The particles are held firmly in place, but they can vibrate within a limited area. As I add increasing energy, the particles respond by moving faster. As they start to vibrate and move faster, we achieve the liquid state. The particles that make up a liquid flow easily around one another. They are kept from flying apart by attractive forces between them. Liquids assume the shape of their containers. As I add even more energy, the particles now gain enough kinetic energy to overcome those interparticle attractive forces and become a gas. The molecules that make a gas fly apart in all directions at great speeds. They are so far apart that the attractive forces between them are insignificant. You could actually flip that around and say they are so far apart because at that temperature the attractive forces are insignificant. What's under the rest of the shade? Well, plasma, but like I said, we're not really going to worry about that because that's physics, not chemistry. So, let's talk about what's called the kinetic molecular theory of matter and how it explains the properties of gases. The kinetic molecular theory of matter is a theory or a model that we use to understand and explain the properties of gases. You may recall early in the course we learned another theory, Dalton's atomic theory, that we used to explain mass relationships in chemical reactions. Again, remember, the theory is a model that we use to explain or understand what we observe in the universe. Okay, remember the natural law is the what? The theory is the why. Okay? And as was the case with Dalton's atomic theory, there are 5 assumptions or parts of the kinetic molecular theory. Remember, these are ideas that help us understand why gases behave the way they do. And here are the 5 parts of the kinetic molecular theory, which I expect you to know. Number 1, a gas is made up of a large number of tiny particles that are so far apart from each other relative to their size that the volume occupied by the particles themselves is 0. Imagine what that means. If you have a balloon filled with helium, the volume occupied by the actual helium atoms themselves is 0. Why? Because they're so far apart from each other. Part number 2, the collisions between the gas particles and the walls of the container are elastic collisions, meaning that when the particles collide, they do not lose kinetic energy. We're not really going to be concerned with that part of the kinetic molecular theory in this course, but later if you take physics, that will become important. Number 3 is important. We assume that gas particles are in continuous, rapid, random motion, and thus they have kinetic energy. Part 4 is also very important. We assume that there are no forces of attraction between the gas particles. Part 5, the temperature of the gas reflects the average kinetic energy of the particles. As the temperature of the gas increases, the kinetic energy of the particles increases, and because kinetic energy is directly proportional to the square of the velocity, as the kinetic energy increases, the particles start moving faster. That's not so crucial right now, but when we talk about gas laws in a couple of days, that will become very important. So now, let's look at some properties of gases that we observe, equivalent to natural laws, and ask the question, how does the kinetic molecular theory explain these observed properties? Let's continue. So, the first property we want to continue is what's called expansion. Gases expand when they completely fill the container, and therefore the gas has no fixed volume or shape. Okay? Here is a diagram that shows a gas occupying one half of a vessel with a divider keeping it in one half. If I remove the divider, what happens? The gas expands to completely fill the container and occupies both halves of the vessels. Sorry about the typo, I didn't make this diagram. So, what part or parts of the kinetic molecular theory best explain why gases expand? Well, let's go back and look and see. Can you think about which parts of the kinetic molecular theory best explain why the gas particles will expand to fill the container? Well, if you said because the gas particles are in continuous motion and because there are no forces of attraction between the particles, you are correct. Let's look at another property. Fluidity. Gases can flow like liquids. I couldn't find a good picture of this online, so I'm going to have to use my bad art to draw it. But if I have a container that contains a gas, and in this case, because the gas remains in the container, it must be denser than air. If I tip it over, what you actually observe is that the gas particles will actually flow out of the container like a liquid. And I have a very, very cool demonstration that I'll show you in class. So, what part or parts of the kinetic molecular theory explain why gases flow like a liquid? Again, if you think about it, you'll realize the same parts that explain why gases expand. The gas particles are in continuous rapid random motion, and there are no forces of attraction between the gas particles. As you'll see, most of the properties of gases are explained by these two parts of the kinetic molecular theory. Let's look at another property. Low density. Gases are about 1,000 times less dense than the corresponding liquid or solid at normal conditions. So let's say, for example, I take a container that is filled with a liquid. Now we can say it's water. And then over here let's say I take a syringe that is filled with a sample of a gas, and I inject the gas into the bottom part of the container. What's going to happen? Well, the gas particles, being less dense than water, will of course rise to the top. Okay? And why is that? What part or parts of the kinetic molecular theory best explain why gases are less dense than the corresponding liquid or solid? Well, because the particles are far apart relative to their size. That is, the volume of the gas particles are effectively zero. Why is that the case? Well, you'll recall that density equals mass over volume. So as the volume of the gas sample itself increases, the density increases. The next property is compressibility. I'll demonstrate this in class as well, but you've all seen this before. If I have a sample of gas and I increase the pressure on it without letting any of the gas escape, the volume decreases. And here shows a cylinder with a piston in it. The pressure is exerted on the piston, and the volume is occupied in the container. As I increase the pressure, the volume decreases. We'll see later in this unit that there is a very simple mathematical relationship between the pressure and volume. You can probably guess what it is. So once again, what part or parts of the kinetic molecular theory best explain why, as the pressure increases, the volume decreases? Well, once again, the gas particles are very far apart from one another relative to their size. If what makes up a gas is mostly empty space, then increasing the pressure means that you can get those particles a little closer to each other without doing any other damage to it. The final two properties are diffusion and effusion. Diffusion is when a gas spreads out and mixes. Effusion is when a gas passes through a small opening. And here are some nice diagrams. So here I have a gas sample in a container. A partition keeps the gas particles on the left side with perfect vacuum on the right side. If I remove the partition, then the gas particles diffuse to fill the container. Now you may be asking yourself, what is the difference between diffusion and expansion? And the answer is not a whole lot. Expansion normally refers to expanding into a vacuum. Diffusion sometimes refers to mixing with other gases. The distinction is not that important. Effusion, on the other hand, is a similar experiment in which instead of removing the partition, I open a tiny, tiny hole in the partition and I observe the gas particles eventually pass through the hole. In either case, the part or parts of the kinetic molecular theory that best explain these properties are, of course, as we saw before, that the gas particles are in continuous rapid random motion and that there are no forces of attraction between the particles. Now, let's sum all this up. All of this leads to the concept of what's called an ideal gas. An ideal gas is a hypothetical gas that behaves exactly according to the kinetic molecular theory. So if you think of those 5 assumptions of the kinetic molecular theory we talked about a few minutes ago, if a gas does every single one of those perfectly, then it's an ideal gas. So, do you think ideal gases actually exist? No, of course they don't, because the kinetic molecular theory is just an idealization. It's useful, though, because as we saw, it helps us explain the observed properties of gases. Okay? Gases that we observe are actually real gases. And a real gas does not behave exactly according to kinetic molecular theory. It is, in fact, a real gas. Okay? But we can ask the question, what kinds of gases behave most ideally? Meaning, which particular types of gases, what properties of gases lead them to adhere most closely to the parts of the kinetic molecular theory? Well, if you go back and look at those again, you'll realize that gases that have small volumes, meaning the particles that make up the gas, the molecules or atoms that comprise the gas, are really, really tiny. And also those gases in which the attractive forces between them are as weak as possible. What are some examples of real gases that behave very ideally? Well, if you look at the periodic table and use your chemical knowledge to come up with some samples of gases that are really, really tiny on the atomic molecular scale and have very, very weak attractive forces, you'll realize that the most ideal gas under any conditions is, of course, helium. It is a noble gas, therefore there are very, very weak interparticle attractive forces, and it is the smallest noble gas. Other gases that are very ideal would include hydrogen gas, and the other noble gases, as they get bigger, they become less and less ideal. Now we can also ask the question, under what conditions will any gas, no matter what its formula or structure, behave most ideally? That is, when will it adhere most closely to the parts of the kinetic molecular theory? Well, that would be under conditions of low pressure and high temperature. Why would that be? Well, because at low pressure and high temperature, the gas particles are the farthest apart. If you decrease the pressure, you increase the volume, and the particles can spread out. If you increase the temperature, you increase the kinetic energy of the particles, they start moving faster, and they have a tendency to spread apart. Under these conditions, the actual volume occupied by the particles is very small, and as they're far apart from each other, you have the weakest interparticle attractive forces. So any gas, no matter what the structure, will behave more like an ideal gas at low pressure and high temperature. In the next video, we will talk in more detail about what gas pressure is, what it means, and how we measure gas pressure. See you then.